Okay, so it's 8 a.m. and we can continue. All right. So where we stopped in the previous class, in the previous lecture, we started looking. Okay, we introduced the Ampere's law, one of the fundamental laws in physics overall, right? And we started looking at the example, and the example was, what if we have a What if we have a infinitely long wire with current, right? And current is distributed uniformly, right? And the wire has, of course, a cylindrical shape, right? And with radius r. Okay, so and we wanted to find magnetic field outside of the wire and inside of the wire. What's that static noise? Okay, thank you for muting yourself. Okay, so we wanted to find magnetic field outside and inside. And in part A, first part, maybe I should write, it's a part A, maybe over here somewhere. Right. Yeah, I think I forgot to write that we are now finding magnetic field outside. And yeah, so what can be applied to find magnetic field? You can use Biot-Savart law. Now we have two alternative ways of finding magnetic field. Either Biot-Savart law or Ampere's law. They're equally great, equally, I don't know, universal, right? But in this case, if you try to apply Biot-Savart law, it will be really, really painful. Okay, not really, but painful. Right. But Ampere's law, here application of Ampere's law are significantly easier, right? Because of the cylindrical symmetry of the problem. Right. Okay, and current, you see, current flows this way, and this is sort of like what we're going to see if you look at the cross section of the wire. So current is out of the board. Right. Okay, so we started applying Ampere's law. So first we started taking care of this linear integral, right? B dot ds, right? And of course, as the first step of application, when you start applying Ampere's law, you have to pick an Amperian loop, right? Without that step, you wouldn't be able to tell which currents are enclosed. Without that step, you wouldn't be able to evaluate the integral because you integrate over an Amperian loop. If you didn't pick the loop, then there's no integral, right? Okay, so since we're interested in the magnetic field outside, of course, it makes sense to pick an Amperian loop outside because basically we're probing magnetic field on that Amperian loop, right? So, and I told you in the previous class, you can pick any Amperian loop your soul desires. You will never be wrong. But if you pick a complicated shape, an Amperian loop of a complicated shape, you will never, okay, you most never, right? You will never be able to solve the problem, right? So on top of being correct, we have to be smart and pick the best possible loop, right, in order to utilize the symmetry of the problem. So we pick a circle centered on the center of the wire, concentric with the wire, basically, right, of some arbitrary radius r small. Right? Then, second step, of course, you need to pick an integration direction for this loop. There are two options, either counterclockwise or clockwise. All right? And depending on that, your current can be positive or negative. Since nobody wants to deal with a negative current, I doubt that somebody wants to do that, right? Of course, we need to pick a integration direction so that the current is positive. Okay, that's what we did. We used right-hand rule number 2. When you curl your fingers around the direction of integration, your outstretched thumb gives you direction for a positive current. So in our case, if we pick this direction counterclockwise, our current is going to be positive. So that's the best option. Of course, nothing wrong if you pick opposite direction like this, right? But in that case, your current will be negative and this dot product will be negative. So you'll have minus on this side, minus on that side. Of course, you will still end up with the same answer, but chances that you're going to lose one of those minuses are quite high. So it's better to avoid making those mistakes, right? So we picked ds as a result, right? And then we justified direction of the magnetic field. Right. Using symmetry, we justified that magnetic field is tangent to our amperian loop, right? And I draw it here and there, right? And after that, I started evaluating this integral. Again, strictly speaking, it's a calculus 3. It's not a trivial integral, but like what we did with the Gauss's law, we're going to do it here. We're going to evaluate this integral without actually taking it, right? Okay. That's why we can use this integral. Okay, so first step, we just showed that B is parallel to DS, right? As a result, dot product gives us just the product of two of magnitude of B and magnitude of DS, because the angle between them is 0, cosine of 0 is 1. All right. So, and as a result, we ended up with this integral. That's where we stopped in the previous lecture. And again, what's the achievement of the first step? Now we don't have vectors. This is in the magnitude of B and magnitude of ds, right? Okay, that's the very important achievement. Now the second step, again, using the symmetry. Look, what if you sit, for example, over here, right? And you see the magnetic field, strength, magnitude of the magnetic field. And of course, what created this magnetic field? Of course, this distribution of current. So if you look from this point at that current, you will see some picture. Remember that picture? And now move yourself, for example, to this point on the amperian loop. And look, will the distribution of current be the same? Will you be able to tell the difference between the distribution of current which you saw from this point or you see from that point? They will be exactly the same. Or if you move yourself over here, and if you look at the distribution of current, it will be exactly the same. It means what? If you have here some magnitude of the magnetic field, exactly the same magnitude of the magnetic field will be there, there, or any other point on the amperian loop. Because distribution, yeah, basically we're trying to utilize the symmetry of the problem, all right? So it means, again, I emphasize we're talking about the magnitude of the magnetic field only, because vector, magnetic field as a vector, they're not the same because of the direction. Here, direction of the magnetic field that way. Here, direction of the magnetic field that way. As vectors, those B's are not the same. But we're talking now about magnitude, and their magnitudes are the same. See the difference? Okay, so now if magnetic field, not if, since magnetic field is constant on the amperian loop, I can write B is constant, and I emphasize on the amperian loop only. If you step away from the amperian loop, for example, step closer, of course magnetic field gets stronger. If you step away, magnetic field becomes weaker, right? But since we picked a circle centered on the wire, so we can use the symmetry. So magnetic field is constant only on the amperian loop. Right? Because sometimes I saw in the past some students will write, because B is uniform. No, it's not uniform. Uniform, it means it's exactly the same at any point of space. But here we're talking about only points on the amperian loop, at all these points. So B is constant only at those points. All right, and it's enough for us because we integrate over the amperian loop. Right? Okay, so if B is constant, of course, it can be extracted. This is the most important step, because you remember I told you in the previous class what is not good about Ampere's law. It's beautiful, it's elegant, and so on, right? But most of the time we want to find magnetic field, and magnetic field is buried inside of the integral. So every time you have to go through the extraction, right? And in this case, it's not that painful, right? So first, it's sort of like a preparation, like anesthesia, right? And then extraction of the truth, right? All right. So now, if we can, since we can extract, so we can write it like this: B times integral over the closed loop ds. And now, you should be able to tell me the answer. What's the value of this integral? In order to do that, you just need to understand the meaning of this integral. Meaning of this integral, you just keep adding small these small ds's, so over the amperian loop. Small ds, I don't know, 5 nanometers or whatever, right? Plus small ds, plus small ds, plus small, plus, and you keep moving around the amperian loop, adding these small ds's, and when you get to the starting point, what will be the answer if you add small ds's? Circumference, the total length of the amperian loop, right? So you will get 2 pi r small. Be careful, because I see when I grade the problem like this on the exams, I see sometimes students write r capital, for example. No. We are on the amperian loop of radius r small. Right. So it is equal to 2 pi r small. So as a result, the value of this integral, I can write, it will be b times 2 pi r. Okay, so we evaluated this integral, so from the other side it must be equal to mu naught times I enclosed. Right. Okay, so now usually after this I asked for find I enclosed current. And as I was warning you when we were discussing Gauss's law, here quite often I see students do the same mistake, make the same mistake. They just solve this expression for IN. So basically they write current, enclosed current, in terms of B. It's not wrong, but it's completely useless. Because our final goal is to find B. B is unknown. If you write your unknown current, right now current is unknown, in terms of our global unknown, again, I would never say it's wrong, but it doesn't give you anything. It's just basically like doing nothing. So right now the goal is to find I enclosed using some other arguments, right? So right now we need to sort of leave this expression for a second alone, right? And find I enclosed. And in this case, the actual answer is quite simple. You should be able to tell me immediately what's the value of I enclosed. Again, what's the meaning of I enclosed? It's the total amount of current physically embraced by our amperian loop. And where that current is within the amperian loop doesn't matter. All right? Look, our amperian loop physically embraces the whole wire. So the whole current I. So in this case, I enclosed is the total current I flowing through this wire. All right? In this case, finding I enclosed is trivial. So in this case, I enclosed equals to I. All right, so now we just need to replace this I enclosed with I and solve it for B. That's it. So that will be the answer for part A. So, okay, let me rewrite it. So B times 2 pi r equals to mu naught times I. Okay, so now we can write B, okay, B as a function of r, because r here basically as a variable, will be equal mu naught times I and divided by 2 pi r. And that's the formula which we started using in our recitation classes. Like, not the previous one, the one before. Actually, for some of you, it was the previous recitation class, right? So, and I told you, getting this formula using Biot-Savart law, it's possible, but significantly more complicated, But using Biot-Savart law, it's basically if I would do it without any explanations, I would do it within 1.5 minutes, maybe. Right. Okay, so that's for magnetic field outside. It's for r larger or equal than r capital. Right. Okay, so now part A is done. Now part B. Let's find magnetic field inside. But again, if something is not clear, tell me. Right. All right, so part B. Actually, you know what I probably should also mention. You remember I told you that if you pick, you have a freedom to choose any amperian loop your soul desire, and I told you you will never be wrong. right? So what if you, for example, pick an amperian loop of an elliptical shape? What would happen with your calculations? First of all, if you had an elliptical shape, ds and b wouldn't be parallel to each other. The first step would be impossible, right? First, then second, if you used an elliptical shape, then b would not be constant on your ellipse, right? Because those points will be different at a different distance. Points of an ellipse will be at a different distance from the center of the wire, and distribution of current will be different if you try to look from different points of an ellipse, right? So both of these steps would be impossible, right, if you used an ellipse. So they were possible because we picked the best amperian loop, right? Okay, so now let's answer the question. Let's find magnetic field inside of this wire. Right, so now let's find B inside. Basically, it means that for R less or equal to R capital. Again, Ampere's law, right? And first step, you need to pick an amperian loop, right? And of course, the amperian loop must be in the region where you want to find magnetic field. All right, and again, you can pick any amperian loop, but of course we have to be smart and we need to pick the best one. And of course, after this, you should be able to tell me immediately that the amperian loop for this part B must be again a circle, but of course position inside of the wire. All right, so let me pick it here. So for each part, amperian loop must be will be different, or is different, right? So this is of radius r small again, right? So that's our amperian loop, or maybe I can write here. So amperian loops. So this is for part A, and that is for part B, right? Okay, so now all these steps we can repeat here. They will be exactly the same. Again, you will pick the same ds, the same direction for the direction of integration. So it will be ds. Then again, you can repeat if you want the same justification. You can justify my direction of the magnetic field. So it will be B for part B. This is B, again, B for part B, right? Right. So exactly the same steps up to this point. Actually, yeah, up to this point. So I'm not going to repeat them. I will just write integral of B dot ds, and I will open my explanation box and write so exactly the same steps. I'm not going to repeat them one more time. So you will end up, of course, with b times 2 pi r, the value of the integral. Exactly the same steps, not a single symbol will be different. And you remember I've done similar, solution was very similar when we discussed Gauss's law. Right? And okay, from the other side, of course, it must be equal to mu naught times I enclosed. So now we need to take care of this, right? We need to find again the next usually enclosed current. And again, don't try to write I enclosed in terms of B, because again, it will be completely useless. Right? So now we need to find I enclosed. And this is the part where lots of troubles, lots of troubles, like with, you remember Q enclosed charge. Here, the same point, lots of troubles with I enclosed. And what we have to use here all the time is only one formula. Definition of current, J equals I over A. Okay, let me frame it. All right. Nothing else. We just need to use this formula over and over a couple of times. Right? So what is this? It's a current density. And current density can be found if you take current and divide it by the area over which that particular current is distributed. So if you want to find current density using this current I, of course, you will take that current I and divide by this cross-sectional area, right? But if you want to use some other current, a part of the current, okay, you will take that part of the current and divide it by the cross-sectional area where that particular current is distributed, right? Okay, so it's all about this formula. Okay, so now before we start calculating, let's see on the picture where this I enclosed. This I enclosed. Again, it's all current physically embraced by our amperian loop. Our amperian loop is over here. So we're talking about, okay, I will use blue now, this current. Okay, current distributed over here. So that's where I enclosed is for part B. You see, of course, it's smaller than I capital or than that I, right? So we need to find only this current. So what can be done? Again, like with Q enclosed charge. Okay, first let me find current density. Again, definition. Using the total current I. So I can write, so J equals total current I divided by the cross-sectional area where the total current I is distributed cross-sectional area with radius R capital. Of course, explicitly we can write it will be I divided by pi R squared. Area over circle. All right. Okay, then if we need to find I enclosed, basically this current, by looking at this formula, what do we have to do? Current equals current density times area over which that particular current is distributed. In our case, it will be I enclosed, this I enclosed equals to current density, which we just found, multiplied by the area over I enclosed is distributed, multiplied by this area, this highlighted area. All right? So I can write, so it will be J times area over which I enclosed is distributed, area of the circle with radius R small. Okay, so now I will take that J, plug it here, and I will get I over A sub R times R capital times A sub R small. All right, okay, so now let's write these A's explicitly. So it will be I divided by pi R capital squared times pi R small squared. Pi gets cancelled. All right, and as a result, we have the expression I times R small squared divided by R capital squared. So that's the I enclosed. I usually do this. Okay, now some students like in presenting it in a slightly different way. It's basically potato, but for some students that second option is kind of better or easier to see. Although it's all about this formula every time. First we use the total current in order to find current density, and then we rewrite this formula to find I, but of course in our case I enclosed, J times A. Okay, some students find this easier. Okay, let me write or. So first, yeah, current density is exactly the same. So we have uniform distribution of current. So first we can find current density using total current, like I've done it over here. Right? Okay, let me write it down. So J equals I divided by pi R capital squared. But from the other side, how else can we find a current density? we can find current density using I enclosed. So we can take our I enclosed and divide it by the area over which that I enclosed is distributed, right? J equals I enclosed over pi r small squared. And since density, current density is exactly the same, we have uniform distribution of current. So if you find current density using total current or current density using I enclosed, it's the same density. These two must be the equal. So from here, we can solve it for I enclosed, right? So from here, we can get, so I enclosed will be equal to what? I, and the ratio of these cross-sectional areas, it will be pi r small squared divided by pi r capital squared. As a result, pi gets cancelled, and we're getting exactly the same expression for I enclosed. Okay, I usually prefer to do this. Some students, when I explain it in this way, they kind of, wow, it's easier for them to understand. So it's up to you. Okay, so now after this, back to our Ampere's law, right? So instead of I enclosed, we need to write that. Right, so now next, B times 2 pi r, I'm just rewriting this, equals to mu naught times, instead of I enclosed, we have I times r small squared divided by r capital squared. Okay, so what can be cancelled? 1r, this r, and that 1r gets cancelled. And as a result, we're getting that b as a function of r equals to mu naught times I, then divided by 2 pi. This 2 pi goes to that side in the denominator. Downstairs will be times r squared and times r. So all this structure is a constant, given constant, mu naught, current is given, r is given, and the variable on purpose I wrote sort of kind of separately to emphasize that when you are, okay, not you are, if you're interested in the magnetic field inside of the wire, of course, a magnetic field increases linearly as you go farther and farther away from the center of the wire. Right. Okay, so now, okay, let me first frame it. Probably first let me write that it's a for r small less or equal than r capital. Now we need to frame it. All right. And now let me plot how magnetic field changes with r small. So plot this and that on the same graph. Okay, so now if we plot it, B versus r. And somewhere over here it's our r capital, radius of the wire. And so let's start with inside. Inside it grows up linearly, proportional to r. So here we should have a straight line. Right. Straight line to the surface till the point, till the surface of the wire. And after that, this is outside, it's inversely proportional to r, 1 over r. So it will decay something like this. Right. So here it's a proportional to r, and here it's a proportional to 1 over r. So that's how magnetic field changes with radius. So that's how we should apply Ampere's law, right? And usually troubles are in finding I enclosed. Some students even have troubles finding I enclosed for part A, but usually not many, right? Usually part A, most of students do well, right? But this part, lots of troubles, right? Although it's all about this, right? Find current density or find current, nothing else. And then you just look at the picture to see where current is, which you're interested in, what's the area, nothing else, right? That's it. Um, and every time you start with picking an amperian loop, right? Amperian loop, and then you can start um, sort of rolling through the solution. Okay, so that's the example. Another example, in my sections, I barely started. In a different example, if there is a concentric hole in the wire. In my sections, I will finish it on Monday. Your sections, yeah, I will talk to your instructors. And most likely, not most likely, I will postpone the homework till Wednesday, this current homework. Okay, so if you have questions, you can ask. Otherwise, I will now switch to the presentation, and we will start moving away from the Ampere's law. So now we can say we more or less know how to use it. Right. Okay, let me turn on the filter. Okay, just a second. Let me. Okay, so now the question for you, all right? About Ampere's law. Because quite often I give a question similar to this on the exam, among multiple choice question. So what do we have here? We have, you see, three currents, I1 flowing into the screen, I2 out of the screen, and I3, we don't have any information about that current I3. Then somebody was nice enough to give us pick for us an amperian loop. You see this amperian loop, closed loop, and you see the direction of integration is given. So it's counterclockwise, right? Okay. And somebody was nice to give us the value of the integral, this line integral of b dot ds, somebody calculated for us. And the value is mu naught times 7. In terms of mu naught is given, right? So it will be easier for you to calculate. So can you, using this information, get all information about that current I3? Basically, can you tell what's the value of that current and what's the direction? Is it flowing in or out? And you see 5 options. Give it a try, and then I will explain how it should be done if you don't succeed, right, in getting the correct answer. Right. Okay, the poll is in the chat. Poll number 1. Right, so I created 3. So just scroll it up slightly. Right, you see concept test 1. Okay, where is my timer? Okay, it should be enough for you to think a bit about this. And now let me do this. Okay, all right. So yeah, it's a direct application of Ampere's law, right? And first of all, which currents are enclosed and which currents are not, because we know everything about the integral. We know the value of the integral. It's a 0.7 mu naught. So pretty much what we have to do, we just need to look at enclosed current, right? And obviously I1 is not enclosed outside. It is outside of the loop, so forget about I1. So we have only I2 and I3. Then are they positive? Okay, I1, I2, is it positive or negative? Okay, we have a direction of integration. So right-hand rule number 2, right? Curl your fingers in the direction of the loop, right? And direction of the loop is like that, right? So my outstretched thumb gives me positive direction for a positive current. So out, the current is positive. Current flowing out of the board is positive. So in this case, I2 is a positive current. Okay, but the thing is, we don't know anything about current I3, and we also don't know its direction. So it's time to use the same trick which we've already used like multiple times. Assume a direction, because yeah, we have 50% chances of getting it right. It's either out or in. So let's assume a certain direction, solve the problem, and then at the end we can adjust it if your current happens to be negative at the end, you can adjust the direction. But if your current is positive at the end, then it means that your assumption about current direction is correct or was correct, right? So let's use that trick. So let's assume that current I3 is out of the screen. So let's make it positive, right? Okay, so let's assume that I3 is out of the page, right? So as a result, now we can write Ampere's law, sorry. Ampere's law. So B dot ds, it's our 7 mu naught, right? So you see 7 mu naught. And then from our speculations, mu naught times I enclosed, it will be mu naught times positive current I2 plus 8, and then positive current I3, according to our assumption, right? So that's what we're getting. So solve it for I3, which is our unknown. Mu naught, of course, gets cancelled, and as a result, we're getting that I3 is -1. Okay, so we see the value of the current I3, it's 1 amp. Minus just tells us that my assumption about the current direction, this current direction, was wrong. So it's not out of the page, it is into the page. Into the page, right? So as a result, that's the answer, and most of you answer it right. Okay, good. So as I said a few times, I give a question similar to this among multiple choice questions on the exam. Among multiple choice questions, because it's quite simple. Calculations are quite simple. Right. Okay, enough of this. Yeah, you have questions?
Into the page.
Why is it into the page?
Yes.
Because first at the very beginning we didn't have any information about current I3, right? But in order to write this side of the equation properly, we had to assume a current direction of I3. Here first I assumed that it's out of the page. Okay, then using that assumption, I wrote Ampere's law and solve for I3. And my answer happens to be negative. So what does this minus mean? It means that my assumption about current I3 direction was completely wrong, right? I assumed that it was out of the page. So if it's a wrong, so there is only a second option, because we have only either out or in. So if out is wrong, the correct direction must be into the board, into the screen. Does it make sense?
Oh, yes. So I2 is out of the page.
I2 is out of the page. You see dot.
Oh.
Dot means out of the page, right? You remember that convention we discussed, all right? How do we show vectors pointing towards you, basically out of the page, or away from you? Just imagine an arrow flying towards you. What are you going to see? You are going to see the dot and the circle in a round. So that's why I2 is out of the page. All right. But for example, this current I1 represented by the cross, it means into the page, because if an arrow flies away from you, you're going to see the cross, basically stabilizers of an arrow, of the arrow.
Right. Okay, thank you.
Yeah, we used this trick already many times, so that's why I was a little bit faster than usual, right? Okay, so next, great. So now we introduced all possible ways of finding magnetic field, right? So, but again, you remember most of the time we use uniform fields. Like you remember in the world of electricity, all the time, okay, not all the time, most of the time, we used a uniform electric field produced by a parallel plate capacitor, right? So every time we assume, let's use parallel plate capacitor with uniform magnetic field. So now we need to introduce a similar device, but for the world of magnetism, a device which will give us a uniform magnetic field. so that we can, I don't know, shoot the particles through that device, right, to see what happens to that particle being exposed to the magnetic field or wire. It's very useful. And in the world of magnetism, that device is a solenoid. See here, I took it from the stockroom in the department a few years ago and keep returning it. So we're going to use solenoid, and the solenoid inside of the solenoid produces uniform magnetic field inside. Right? And again, what is a solenoid effectively? It's just a helical coil, right? So if you take a piece of if you take a wire, right, and wrap it around a cylindrical surface, right? Okay, you're getting a solenoid, helical coil. Okay, so now let's try to sort of justify why is it going to give us a uniform magnetic field inside. Okay, so steps. Sort of I divided process of sort of building a solenoid in a few steps. First, let's take an infinitely long straight wire. Okay, that's what effectively I have right now. It's a very long cord. It's a charging cord, right? Some smartphone or something, right? Okay, infinitely long. So what can we say about the magnetic field created by an infinitely long straight wire? There it is, right? So magnetic field lines are circles. We discussed it in previous class, I think. No, the class before that, right? And how can we find direction of those magnetic field lines? Outstretch your thumb in the direction of the current, and your curled fingers gives you curled fingers give you direction of the magnetic field lines, right? Okay, so that's by an infinitely long straight wire. But what if I bend? What if I make a loop out of this wire? First loop. I'm going to get, as a result, something like this: magnetic field lines. So when you are closer to wire, it's still kind of circular. But as you move farther and farther away, and you will see circles becomes more and more distorted, right, with very large radius. And if you look at the center, for example, if you take this point equidistant from both wires, so what are you going to get there? So you will get two magnetic fields created first by the top wire. Magnetic field created by the top wire will point that way. Then magnetic field created by this bottom wire will point this way. All right. And the same in magnitude. If you add them up, of course, you will get magnetic field, horizontal magnetic field. And if you step away, for example, from this point, right, if you step up, all right, of course, contribution from the top wire will be stronger, so magnetic field start bending sort of that way. Or if you step away lower below this line, of course, magnetic field gets bended and start pointing that way. Sort of, you will get magnetic field lines similar to this. Okay, now next step. What if I create the second loop? So first I created the first loop. Now what if I create the second loop? And then the third one, and the fourth one, and so on. If I keep adding and adding those loops, right, what I'm going to get at the end. So all these magnetic field lines are going to be squeezed inside between these loops. And you will get, after, when you create many loops like this, you're going to get magnetic field lines of this shape. And if you look reasonably deep inside of the solenoid, magnetic field is uniform. Density of magnetic field lines are going to be approximately the same. Okay, not approximately, very, with very good approximation will be, density will be the same, right? But of course, as you move closer and closer to the edge of the solenoid, of course, density of lines, magnetic field lines becomes different. And of course, it means that magnetic field is not uniform, So in order to have a nice uniform magnetic field, the length of the solenoid must be significantly larger than, for example, diameter or radius of the solenoid, right? In this case, this solenoid is reasonably good, right? if you're interested in the magnetic field, for example, in this part of the solenoid, it will be a reasonably nice uniform. It will give us a reasonably nice uniform magnetic field. So from now on, most of the time, uniform magnetic field will be produced by a solenoid. And look, what is interesting also, magnetic field just outside of the solenoid, you see, B equals 0. B inside constant, outside is 0. It's similar to the electric field created by a parallel plate capacitor. You remember parallel plate capacitor? Electric field inside of the capacitor is uniform constant, right? But outside of the capacitor, electric field was 0. And the same as a solenoid, but of course now we're talking about magnetic field, right? Okay, so now it can be shown if you take some liquid and spread on the surface of the liquid some iron filings, right? And then put a solenoid inside, right? So those filings, right, made of metal, of course, they basically work as small compass needles. And of course, they orient themselves along magnetic field lines. And as a result, you see over here lines representing magnetic field lines. You see between, in the solenoid, you see magnetic field lines with equal density, giving us inside magnetic field inside is uniform. But if you look outside, just outside of the solenoid, you see all those filings kind of randomly distributed in all possible directions. It means what? It means that magnetic field is 0, so they just normally randomly distribute themselves on the surface of water, right? Okay, whatever liquid is used, right? Okay, so that's sort of kind of justification why a magnetic field inside is uniform. And now the next step will be your quiz number 5. Usually I give this as a take-home quiz, but in this semester all quizzes are take-home quizzes, right? So at the very beginning I use this slide to derive an expression for the magnetic field inside of the solenoid, because now we know that magnetic field inside of the solenoid is uniform. But again, we need an expression so that which can be used to find the value of that magnetic field. And I used to use this slide to derive it. But for PowerPoint presentation, it's too much of math details, right, in order to discuss it. Every time I didn't feel right discussing this slide. It's too much. As a result, now I decided, okay, a few years ago, I started giving it as a quiz. So what you have to do, you can use this slide. Of course, it will be posted in the Blackboard, or you can use any book you want. Your goal is to derive this formula, magnetic field inside of a solenoid, right? So you need to draw a nice picture and use Ampere's law. Right, you see Ampere's law. Pick a loop. You see this rectangular loop, right? Divide this integral into 4 integrals. Show directions of B, ds. Show that some integrals will be 0, some is not, and derive that formula. A reasonably simple assignment. You just need to work it out, read, or again, either my slides or a book, and get that formula. Of course, this formula will be used a lot by us, right, in the future. Okay, so I will send you email about this quiz also, and the deadline, I will think about that deadline, right? Okay, so pretty much at this point here, it's 8:50. Just an application of the solenoid, the most kind of famous application, it's an MRI machine. Right. Why this MRI machine had this cylindrical shape? Because basically person is positioned inside of the gigantic solenoid. Right. Gigantic solenoid inside of the reasonably strong magnetic field, 1.2 Tesla, it's a strong magnetic field. And in order to get this strong magnetic field and this high current, usually liquid helium is used. It's only one of those rare devices where industry, okay, medical industry basically accepts usage of liquid helium. Liquid helium is so damn expensive, right? And so evaporates so fast. I boiled lots of liquid helium when I was doing my PhD, right? So I know, and of course it's very expensive, right? But because MRI machine is so useful, yeah, hospitals take those expenses, right? Okay, guys. All right. So next class we will start. No, yeah, next class on Tuesday we will start discussing magnetic force, maybe in our recitation classes, right? Even.